So we were starting to understand the Dirac theory. Okay, so we were looking at we just started with the Dirac theory, and we noticed that the Dirac theory starts with the assumption that maybe because we have to in quantum mechanics all the operators are linear operators, maybe one should not start with a quadratic dispersion relation. Now we start in classical mechanics we have p square by h cross square by p square by 2m plus m, essentially p square by 2m, E is equal to p square by 2m, then energy operator is always linear. Okay, so it is always E is equal to p square by 2m, but the problem is not with the momentum operator. Okay, just to clarify again, essentially, so the energy operator has two eigenvalues or two values essentially, which are plus and positive and negative for the square root of p square plus m square. Now the moment you put square root, then you cannot really expand the square root because it becomes a nonlinear operator, and several problems exist essentially. So if you directly do with the E square is equal to p square plus m square, you end up having other problems, like for example what we have seen with the Klein-Gordon equation essentially, and the negative norm probability, the Klein paradox, and so on, so essentially, and Klein paradox. So what was Dirac's idea? Dirac's idea was that, so suppose I do not take the energy operator to be quadratic, I want it to be linear, and but without a square root factor for p and m. So he started off by writing this particular relation essentially, that you take E is equal to p plus m, but now E and p and m are multiplied by some operators alpha and beta, which are nothing but some matrices alpha and beta. And what we have seen is that in the previous class, what are the conditions on alpha and beta are essentially. So alpha and beta should, now how do you get these conditions? You get the conditions that if you square the E square operator essentially, you should get back p square plus m square essentially. You should square the E operator, so you should get back E square is equal to p square plus m square, which is the correct relativistic equation, Now but you are fixing your alpha and beta such that they give you the correct equation, relativistic equation, by making an assumption of the form which I have given, which we have written here essentially. And so when you put that back into this essentially, you get these conditions on alpha and betas, and beta square is equal to 1, alpha square is equal to 1, alpha beta should be anti-commuting matrices essentially. They are anti-commute, alphas anti-commute within themselves and also anti-commute with beta. And then we have seen that they should be either dimension should be even, because if you take the determinant essentially, you end up seeing that their eigenvalues should always be plus or minus 1. So the dimension should be even, and the second condition is that if you take the trace, you see that they should end up having essentially they should end up giving you okay, they should be traceless matrices essentially. Okay, they should end up being traceless matrices, and that is what should give you a condition that they should be even traceless matrices, and they are also Hermitian essentially. And such kind of matrices which are traceless, Hermitian, and determinant plus and minus 1 are already known in quantum mechanics in dimension 2, which are called the Pauli matrices. But instead of 4, which we need 4 linearly independent matrices to satisfy the Dirac condition essentially, which is E is equal to alpha times p, because there are 3 p's, px, py, pz in 4 dimensions, and 1 for the mass. Instead of 4, you only have 3, and these 3 are your Pauli matrices which are given in this particular fashion. So, dimension 2 for the size of the matrices will not work, and you can resort to linear algebra, where we can see that the number of independent Hermitian matrices in any n dimension are given by n square minus 1, and so you will end up having only 3 for n is equal to 2. In n is equal to 4, there are 15 such matrices possible. So, you think that they may work essentially. That is precisely the solution essentially we got, that one of the solutions would be that if a beta is given in this particular fashion 1 0 0 minus 1, which is Hermitian, traceless, and determinant is equal to plus minus 1s. Okay. This satisfies all the conditions, and similarly you also have alpha I defined in terms of the sigma matrices, in terms of the 2 component sigma matrices. So, which is 4 component, it is a 4 by 4 matrices with the upper 2 by 2 given by one of the sigma matrices. So, each alpha is essentially sigma 1, alpha 1 is equal to sigma 1 in the off diagonal essentially, alpha 2 is equal to sigma 2 in the off diagonal, and alpha 3 is sigma 3, and this will satisfy all the conditions essentially which we have listed above essentially. Next, very good. Now, we have found what alpha and beta are, and now that there is such a possibility, okay, such a possibility that these matrices, such matrices can exist, now we can write the operators essentially, quantization conditions on this particular case. So, you have, so we can have this relation is valid, okay, this relation is valid. Now, what we have shown is that this relation is valid for dimension alphas of for alpha and beta belonging to dimension 4, and one such example is this particular case which we have seen essentially. Good. Now, what is the quantum mechanical operators which we can use? We can use the quantization conditions which we can have E is equal to I del by del t, the operator form, and P is equal to H cross del. Okay. Putting this back, okay, now be it set I let me write it in terms of H cross is equal to 1. So, this is just becomes I del minus I del okay. Putting back into this, I get the relation essentially now. This is the famous Dirac equation, okay, and this is the famous Dirac equation. Now, you can do much further essentially, you can remove this constant, this thing beta in front of m can be removed, okay. We can introduce some other matrices which are called the Dirac gamma matrices. So, that the equation becomes even more compact. These are again 4 dimensional matrices which are given by gamma 0 is equal to beta, gamma I is equal to beta times alpha I. So, what we did, okay, essentially is multiplied by beta all through, okay, we multiplied with beta all through, essentially, this just becomes gamma I, and the m can become essentially coming from del 0 essentially. and you can take the left hand side here, essentially you can take it to the left hand side, you can take it to the left hand side, so that you can write it in a covariant fashion. You can write it in much nice form. So you have now alpha 0 is equal to gamma 0 is equal to 1 0 minus 1, and gamma I is equal to 0 sigma I minus sigma I, because remember beta contains minus sign for the lower 2 by 2 matrices essentially. So given this form, taking the delta to the negative side, essentially to the negative side, and we can write the entire equation, which is the most famous equation in relativistic field theories or in quantum mechanics in general, is equal to del by del mu del x mu minus m psi is equal to 0. This is the famous Dirac equation. So gamma 0 is del by del t, essentially I del cross del by del t, we get this particular thing on the left hand side, gamma 0, and del by del x essentially with a minus sign will give me IP, okay, in the momentum frame, essentially it gives me IP, I or minus I del cross nabla or whatever, and then minus m is this particular m which contains with the beta function essentially. So you end up having a negative sign for the mass essentially, okay. This is okay the condition for the this is the condition, this is the equation rewritten, where we have taken everything on the left hand side, we can take everything on the left hand side, and we put a very nice form which is really manifestly covariant, okay, and which is this particular thing. This representation of the gamma matrices is called Dirac representation. As we will see, there are several representations of the gamma matrices that are possible, which is not surprising because we have seen that n is equal to 4 has several 15 possible Hermitian matrices essentially, okay, 15 possible Hermitian matrices. So there is a possibility that there could be other representations also for the gamma matrices essentially. So now what are the commutation relations between the gamma matrices which has to be satisfied? So the gamma matrices has to satisfy a simple commutation relation which can be written in this particular fashion. So this is gamma mu gamma nu, okay, to eta mu nu. Eta mu nu is the metric. So by particular choice, sometimes you can also call it as G mu nu, okay, in 4 dimensions, and this is flat space metric. So this is either 1 0 0 0 0 minus 1 0 0 0 0 minus 1 0 0 0 0 minus 1. So this is one of the representations of the eta essentially. So by choice of the eta, meaning of the metric, essentially you fix the metric and the gamma matrices should satisfy what your equation is essentially. These are the satisfaction, and this is the first time we see in the position space the relation which we call the equation which we call as the Dirac equation, okay, the Dirac equation. So now we can write it even more compactly like people do essentially. So you can write gamma mu del mu as del slash. So, this product is called del slash. So, in that case this equation becomes extremely simple. Fantastic. Okay. Okay. This is the most famous Dirac equation for a pre-particle. Now, the first thing, now let us go through this thing. Okay. Now, the first thing which we see about this equation is equal to that this equation is a not a this equation is not a scalar equation. Here what I mean, it is not a Lorentz scalar essentially. Now, how do I know that? Because this is it is not a scalar, because gamma 0 is a matrix. So, we had to know whether it is covariant or not essentially. Okay. We derived it in a very covariant fashion, in a Lorentz invariant fashion essentially, but it is not clear that okay, this equation is a Lorentz, it is a matrix essentially, it is not a scalar. So, what I mean say is that it is not a scalar. Okay. So, now let us expand I del slash is equal to I gamma mu del mu. It is always interesting to do it because we have to see it essentially, how does it work essentially. So, that is I gamma 0 del 0 minus I gamma I del I. Okay. This is nothing but del slash essentially. If the metric is given in this particular fashion, I can expand it in this particular fashion. Okay. Now, gamma matrices we can re-express it in this particular fashion. So, you have gamma matrices as, remember, I times this is a 4 by 4 matrix given with beta. So, this is nothing but, again remember, gamma is equal to beta, beta is equal to 1 0 0 minus 1 essentially. So, and gamma where is gamma, gamma is equal to 0, gamma is 0 is equal to beta. So, this is 1 2 by 2 0 0 minus 1 2 by 2 times del 0 minus I 0 sigma I minus sigma I 0 del I. Okay. Or del I, you can write it in terms of del I. Now, you can express this, and then you have minus m times 1 essentially. Okay. So, there is, this is nothing but your okay. So, the first thing we notice is that this is a 4 by 4, okay, and then m is equal to m into 1 by 1. So, this is all 1 by 1 matrices. So, this can be written in terms of just writing in terms of 2 component form, 2 m's essentially, this is equal to 1, okay, m. So, the total left hand side, okay, is given in terms of I del slash minus m is given in terms of a diagonal form which is I del 0 2 bit. I will expand it into 4 by 4 later, but it becomes sense minus m minus I d 0 minus m. Okay. This is 2 by 2, remember this is into 1 into 2 by 2, 1 into 2 by 2, and then there is minus I sigma I del I plus I sigma I del I. Okay. So, this is the form which is written in terms of 2 by 2 matrices for the Dirac equation, okay, on the left hand side essentially. So, what should be the wave function? What should be the wave function? Okay. Now, again let me just repeat it again for purposes. I expanded del slash, okay, where the Dirac equation can be written in a very extremely compact fashion as I del slash minus m psi times is equal to 0. Okay. Now, I expanded gamma 0 del mu is equal to gamma 0 del I minus gamma I del I. Now, gamma 0 del 0 is written in terms of 1 by 1 minus 1 because this is nothing but your beta matrix, whereas this is nothing but beta alpha I. So, this is given in terms of sigma matrices essentially. Now, here I replace del I with the Laplacian essentially, not the Laplacian, the del I derivative, and the m I wrote it in terms of 2 by 2, 2 by 2, okay, unit matrices exactly like here, okay, and then I wrote this entire thing here 2 by 2, sorry, okay, in this particular fashion. So, this is I del slash m on the left hand side. This is called the Dirac operator. Is a 2 by 2 matrix given in this particular fashion essentially, or it is actually a 4 by 4 matrix if you expand the sigma matrices and the 1 by 1 2 by 2 matrices essentially. It can be written in terms of a 4 by 4 matrices. Now, the reason I wanted to write in terms of 2 by 2 will be evident later on when we start looking at the solutions essentially. But already you can see that there is a distinction between the signs of the upper 2 by 2 and the lower 2 by 2. So, the upper 2 by 2 has minus 1 essentially. So, there is a minus I del 0, okay, there is a minus sign here missing, minus I del 0, okay. So, this minus sign can be pulled out and this will be a plus sign, okay, or we will write it again essentially, okay, minus I del 0 for the diagonal parts, and then and the off diagonal parts also a relative minus sign. So, there is some off diagonal parts also, there is a relative minus sign here, there is a minus sign here, and there is a minus sign here essentially. So, this is precisely why we want to write it in this 2 component form. Let me write it again essentially. This is nothing but I del 0 minus m into 1 by 2 by 2 unitary matrices and minus I sigma I del I or derivative I essentially I sigma I del I This I can write it in terms of sigma bar dot del bar okay. These are 2 by 2 matrices anyway, this is nothing but 2 by 2 matrices. So, this is the Dirac operator, okay. This is the Dirac operator, and this Dirac operator has a relative sign difference in the diagonal part and also in the off diagonal part between upper type and down type essentially. Okay. Now, this is not an overall minus sign, as you have seen essentially that definitely the diagonal part is not an overall minus sign, okay, whereas the off diagonal part can be thought of as an overall minus sign essentially. So, for the diagonal part it is not an overall minus sign, that is something which you should remember. Now, the question we were asking is what should be the wave function, and the wave function is should be because this is a 4 by 4 matrix and the right hand side, okay. So, should be 4 times 1, okay. It should be a 4 times 1 column vector, okay. Essentially should be a 4 times 1 column vector such that the right hand side just goes to 0 essentially. So, you have this 4 by 4 matrix and this 4 times 1. So, the wave function is a 4 times 1 column vector, so that the right hand times goes to 0 essentially. So, what is this column vector? This column vector is nothing but your wave function, but the wave function is 4 component, has 4 components. So, it is a 4 by 1 column vector, it is a vector. So, the 4 function is a vector. So, I should write it as with 4 components psi 2. So, whereas this matrix is nothing but your matrix this particular fashion. So, this is what comes here. So, let me write it down explicitly again, I del 0 minus m times 1 2 by 2, this is be a upper 2 by 2 part essentially. Okay. Okay. I put this breaking into 2 by 2 components and we will see why this is later on essentially. So, the wave function is a 4 component vector. Okay. So, it is a what kind of vector we will see, it is not a Lorentz vector as we will see later on, it is a vector in the gamma space essentially. In the gamma space in the sense that it is a vector in not a Lorentz vector because it does not have mu indices, okay. The wave function is a 4 component vector in a vector space spanned by gamma matrices, okay. Because this expansion we did in gamma matrices, remember this is not Lorentz matrices, okay. So, this is not mu index or anything, we multiplied with mu index essentially, but each that mu index, it is a scalar equation essentially. If you write it in this particular fashion, okay, this looks like a scalar equation, okay. this is Lorentz scalar like equation, essentially it looks like a Lorentz scalar, but it is in a space given by these gamma matrices. This vector the wave function psi is a vector in the space controlled by these gamma matrices, okay, in a linear vector space which is concerned by these gamma matrices, and such a vector is called a spinor. Such a vector is called a spinor. Okay. Okay. So for the first time we have seen what the wave function of a Dirac equation should look like, and we call it is a special mathematical object which we call it as a spinor, because it is like wave functions, okay, it is like wave functions which is it is a 4 component wave function, but it is not a wave function of any scalar equation, essentially like Schrodinger equation or Klein-Gordon equation or something essentially, but it is a wave function in a space which is spanned by gamma matrices essentially, because the gamma matrices sets the dimension of this Dirac equation essentially. And so this has a special name which is a vector in the space spanned by the gamma matrices. So this is not a Lorentz vector, it is a special case which is called a spinor, and now we will start seeing more and more details about these wave functions essentially in the next lecture essentially. Okay, I will stop here essentially.